So it is physical chemistry class. We have a goal to predict properties of molecules and materials by modeling, or at least to understand, interpret what is going on. And we have our main focus is wavy nature of electron. You got all core knowledge on the main principles, and now we are trying to apply it to electron in free space. We are going the path of true science by analyzing it with fresh brains and trying to make hypothetic answer, like formulate question, formulate an answer, and then do boring math to prove it right or wrong. With time, we will go through MATLAB skills, and we will often try to replace boring math with just a couple of commands with computer, but by now we still need to practice a little bit. And I do not have a goal to scare anyone, but by looking through this sometimes long derivations, one may come to an idea that yes, running computer codes is preferred. So there were two. There were two attachments to today's email. One with the notes that I'm going to show, and today they're messy. I didn't have time to retype things nicely. And the second one is surprise quiz, which is not a surprise anymore, and we will do it on the Google Docs. So you have your computers with you. You can just prepare them. We will do it in about in the middle of the meeting. So I will mumble some equations related to predicting free electron, and then it will be like a crossword, placing a couple of pieces of equation in the right spot. So it shouldn't be too challenging. So a little heads up about last and future labs. I do not have power to mandate any more than 3 hours of your presence in the class. So in some sense, the labs are optional, but on the other aspect, some of the materials offered in the lab is not doubled in the lectures, and it will be towards your credits. So it's just beneficial. Next lab, we will do a review of everything what was on the first and second. So if you miss first and second, just log in or join, you'll be fine. And on Monday or so, I will circulate a sign-up list where we will make another set of presentations sharing with each other MATLAB skills, because they will be really useful for the rest of the class material. So we are progressing through the second chapter, and we are going to practice the third way to predict future for this electron in free space, basically plugging in basis sets of plane waves and accumulation and finding expansion coefficients and see what happens. So if you are online, please email this homework one. If you are in class, you can just hand me a piece of paper. And the second work, we probably need to briefly chat more about it. So if you do set of sines and cosines, this sines and cosines on the interval from 0 to 12, you will go half of the camel's hump, 1 hump and 1 minus hump, then 3, 2, and one needs to integrate from 0 to L. And when you integrate multiplication of this function by something different from L over 2 to L, it will be already 0 for sure. So it actually needs to tailor the integration limits from 0 to L over 2. Show Hamiltonian operator for the plane wave. If we will carefully follow today's meeting, it will be just cut and paste from the lecture. Find projection of Gaussian wave packet, which is not an eigenfunction of Hamiltonian, like from the lecture. Find projection of Gaussian wave packet, which is not an eigenfunction of Hamiltonian, like yeah, onto plane wave, which is an eigenfunction of Hamiltonian. So it's our third way to predict future, or to find expansion coefficients. We multiply wave function of the past by the basis function and integrate. So there, today during the lecture and on Monday, I will give the answer to this number 3 and assume that you know how to do it. Because otherwise, this is not ideologically, philosophical, complicated, but it is lengthy derivation. It will take like 30 minutes. And I will assume that answer is known and you'll do an inverse operation. But ideally, everyone will complete it by Monday. And if you find online, this is very standard trivial integral that many people did it in the last 2 centuries. And there are traces of it in the Wikipedia, if you just look on YouTube. So you can either derive or find and just show derivation. I don't care. If it will be too challenging, well, try your best. And in one of the coming times on the lecture, I will, just in case if it was not super successful, I'll show how to do it by pen and paper. It's quite fun if you like math. If you don't, you can tolerate it. It's not the worst thing. What did we do last time? No, it is what will be the last slide of today's meeting. So if you expected result. I will not play populism and invite you to leave the room if you understand the slide, because it is not the final answer. We will do slowly but surely through this problem. Again, it is a problem for several lectures. We want to predict what would happen to a localized electron in the free space. And on the lectures, I will assume that we already know the expansion of this initial localized Gaussian function over plane waves. But now we will need to construct it back. And in some sense, the whole lecture will be just to chew around, to discuss around and explain how we practice this conversion from past to the future. So we'll do today. We'll do everything except past integral. And if you look carefully or not carefully on this expansion, you recognize here is our basis functions, phi k of x. Here you probably will not recognize, but it is my task to show that it will be eigenenergies E sub k. And this stuff, it is the answer from the homework that I hope very much that you will be able to derive this equation. But if you will not, I will tolerate and show how to do it. Just try your best. And we are practicing third way to predict future by multiplying space-time, space part, time part, and expansion coefficients. And since there, well, I'm going too far, too quick. since amount of plane waves is not discrete, so that since they are continuously changing, one can assume plane wave of any wavelengths. Instead of summation, we replace it by integration. And then mathematically, one can, this is correct, but ugly because it is too long. And all human beings are naturally lazy, at least most. If there are good exceptions in the class, they will applaud, but I'm not an exception. And to make this equation simpler, one can replace everything which is not integration variable by a constant. So we have integration variable squared and integration variable linear, and things in front of them are replaced in this way. And then basically when we need to take only this input. So this is the last point of today's meeting and first point of Monday meeting. So my goal is just to arrive to this point, and to some sense it is more or less evident, but let's go slowly but surely. I'll just check if anyone types. No one is typing. No, oh, August has connected. Hello, August. And I'll check if there is anything in chat room. Okay, nothing in chat room. Let's continue. But if I miss something in the chat room, please switch on microphone and speak up, because I cannot promise to check it every minute. And last Wednesday, I think the voice was not recorded. I forgot to put on microphone, and one of the remote attendees was typing messages, but I was not seeing and not hearing it. So let's practice laziness. My original plan was just leave a blank screen and invite people from class or write myself, but we are adults. We can leave this things for later. So what is kinetic energy? If in your high school physics?
Energy that is in motion.
Correct. And what is the equation if you know velocity or momentum and we know mass?
1/2 mv squared.
Super. You, I can believe you got A in physics in high school, or maybe in college physics as well. So momentum is mass times velocity. Therefore, if we change your mv squared over 2, if one replaces v as p divided by m, then one gets this p squared over 2m, right? Kinetic energy. Now, we did agree that momentum is the derivative over space. So if you want to be advanced quantum theorists and physical chemists, we may want to plug in this P into this P. And then instead of classical kinetic energy, we will get quantum kinetic energy. Make sense? And now here is just a boring thing. So imaginary unit squared, Planck constant squared, 2 masses are leftovers from classics, and 2 derivatives over the space, or 1 second derivative over space. So my imaginary unit squared is -1. Here is another 2 minuses. So minus 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 will be 1 minus. So minus h bar squared over 2m, second derivative over space. Congratulations. You do know Hamiltonian of the electron in the free space. Hamiltonian is summation of kinetic and potential energy. And since I did set up the easy problem. Free space means there are no barriers, there are no walls, there are no ions. Nothing is attracting or repelling out. It's free, which means it can have only kinetic energy. Potential energy is always zero. So kinetic energy is the whole story. Therefore, we put H equals this stuff. Make sense? Good. So again, I do not have time and wish to play kindergarten, but it is a little option. So imagine I wiped off colorful ugly writing and left only black ugly writing. And then our goal for the day is to fill the spaces. So our third way to predict the future is put Eigen functions, the accumulation of phase, which is minus I h bar Eigen energy times time, and then multiply C sub k, which I will borrow from your homeworks that you hopefully can on Monday. So in order, if you want to be rigorous, in order to find these eigen functions and eigen energies, we need to solve which equation? Let me simplify. Which version of the Schrödinger equation we need to solve? Time dependent or time independent?
Independent.
Yes, correct. Because this is solution of time dependent already. So if it builds on time independent, and here it is, right? So we need to take Hamiltonian from the previous ugly slide that you agreed on, and so find which functions, which energies will it provide. When we did introduce a concept of eigenvalue problem, we did a little example of reverse engineering, assuming that we have plane wave function and checking that it is an eigen function of the momentum operator. If you remember, if you don't, do it work. We will play the same game. We will guess that plane waves are good candidates to be eigenfunctions. And if this hypothesis is correct, then to find eigen energies, we just need to plug plane waves into this equation and see what happens. And just a little note, I hope no one has a blow out of mind, because we are using the same words, eigenvalues and eigen vectors, for both discrete things in MATLAB sessions on Wednesdays and continuous things here. At some point, we will merge them and use the same common names for objects of different nature, but basic laws of math and quantum theory will be applied to very heterogeneous systems. So it may sound a little off at the beginning, but then you'll get used. So here is the plane wave, right? Here is the Schrödinger equation, which the Hamiltonian is here. So when we want to practice second derivative, maybe it is already on the next slide, but let me do it, and you can try it. If you start, you will do it quicker than I. Just know that your brains are fresher. So minus h r square over 2m stays here. Then if I can do it one derivative and then another derivative. So here I'll put what comes as a first derivative of exponential. So everything which was up front was in the power comes up front, and the exponential itself stays exponential. Kx. And if I practice derivative once again, then minus h squared to m. And then I will get minus I once again and k once again, right? It will be minus I squared. And also in the denominator, I will have k squared. So minus I squared will be minus 1, right? And it will compensate this minus that we used to have over. So overall sign will be plus, because minus will be plus. And we will have k squared over 2m on the left. And on the right, we will have E sub k equals plane wave, right? Now we can cancel plane wave on the left and right and get that E sub k will be equal h bar squared k squared 2m. I hope very much that this result doesn't differ from the previous year, and if I flip the slide, it will see the same. Maybe in a better writing. No. It's quality of writing is not better, but the idea is the same. I don't know why it took so long to prove. Maybe I was trying to repeat it. But you've got the idea. I don't need to repeat. So once again, Eigen energy h bar squared k over 2m k squared. So we are approaching our goal. So our goal is to plug in 3 things into the protocol to find solution of time-dependent Schrödinger equation. We need eigen energies, which are here. We need eigen functions, which are plane waves, and we need expansion that we will just borrow from the future, from the whole. Okay, so here is your homework. And I will not show the solution not to steal your fun, but what you will be doing is just taking plane waves, multiplying it by Gaussian function, and integrating. Gaussian function looks like a Mexican hat, sombrero. So first 2 things are reviewed. Imaginary exponential plane wave. The imaginary unit, time, h bar, which comes from general protocol, and then the value of energy, right? So the value of energy is this wave number squared, h bar squared over 2m. And you can see that probably one will be able to cancel 1 h bar in the denominator and denominator. So if you're taking notes, it's prudent, because soon during today's meeting we will do a surprise quiz, or you basically will try to type in this stuff into empty boxes. So here is how my wave looks like, and here one can simplify by having only 1 h bar in the denominator and no h bar in the denominator. And time must be here. It must be imaginary, and it should be quadratic in the index of energy. So here is the answer to your homework. I will discuss its functional form and how to interpret it. So the Gaussian wave function in Cartesian coordinate space was Mexican sombrero. Now we are coming, how to say, to space of these indices. C sub k, it's like function of k. And if you carefully do it, it will be again a Gaussian function. If you have a discrete set of k's, it will be values of this C sub k will be small, then bigger, 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 and then again smaller, smaller, smaller. If we carefully do it mathematically, it will be exponential minus k squared. And interestingly, the width parameter that was in the denominator of power of exponential now comes to numerator. So this is the main change in functional form. So we go from Cartesian space to space of Eigen functions. And if one does everything carefully, there is a square root coming in front. A little note. I don't have doubts that if you invest time, you'll do it, but just to think that you feel more comfortable, and if you decide not to solve yourself but look online, the integral of Gaussian wave functions does not have answer in formal formula if your limits of integrations are indefinite. So like if you integrate x, you get x squared over 2, no matter what is on the limits. For Gaussian integral, the answer is available only for known limits, for certain limits, and specifically for limits going from minus to plus infinity. So it is, if you look on tables, one should first check what would be the integral of e to the minus x squared. And then the trick is to change variables so that it will be e to the power minus new variable squared. Okay, basically line the strategy. Okay, but today our task is more humble and less ambitious. We just need to take this little piece and plug it into our protocol for solving time-dependent Schrödinger equation. So here is the solution of the homework. Something is repeating this. And here is what we are going to solve. So we will need to solve summation for the plane wave, energy, and solution of the homework part. Let me make a statement that you may already agree with. Just repeat. When we formulate plane wave, the symbol k determines how sparse or dense are the fringes. So this exponential wave is a helix, or if you take real or imaginary, it will be oscillations. And parameter k tells whether they are, how many coils per meter or per inch, or dense or sparse. In this specific problem for free space L, for this type of equation, there is no quantization in a narrow sense. There are no restrictions. There are no limits for possible values of this variable k. We can coil this wave function as dense or as sparse as we want, right? There are no restrictions to have plane wave of any wavelength. So it is a problem with continuous spectrum. And therefore, if you need to make summation of this eigen values and eigen functions of any possible k, which is continuous real number, we can replace summation by integration. So wherever was sum, we put integral from minus to plus infinity to k. Why we have minus? Because plane wave can correspond to motion forward or to motion backwards. So we start with very quick motion backwards, then going to close to zero when it doesn't move, very sparse fringes, and then we go to very quickly going forward. So replacing summation by integration. Okay. No. Now we need to want to keep annotation. Yes. So let's please open your links to the Google Doc. And if you see the name is already filled, then go to the next one. So I see Zane did start it, Jared did start it, and I invite, let's see who is online. August, Spencer, and Tim. Please try to follow this link and fill it as well. It will be humble credit less than homework, but try to do it. So just in case, let me share the link and probably copy. And I can put it in the chat line just in case if and like it in the email.
You type, how do you get type in the box?
Insert a text box.
Okay. I don't see. Oh, okay. It's only me, Zane, and Jared. Or no, Tim is also doing it. Yeah, thank you, Tim, for joining in the assignment and trying to do it. So we have 3 brave attendees. Spencer and August, you're, oh, okay, now I see more people are connected. Let me see, maybe it is a lower through the list. Yes, I do see Spencer. I do see someone is on slide 5, but there is no name. So if you are watching or taking notes, it shouldn't be too challenging. So wait a little bit, and then we'll go and compare. And it is not a major challenge in the class. We just need to check that we all are staying on the same page. Power IKX. Yeah. And someone is trying to find an empty spot. Here it is almost done. Jared is still thinking. But if you were taking notes, it should.
Sorry, it's taking me a while to type all this out.
Yeah, typing is challenging. Maybe one can. Yeah, typing is better. I do not think annotation will work well here. And I hope you do not mind that we play this game in the open way, because these answers are not big secrets. Who is on the team? If you do not remember, or if you do not have notes in front of you, for expansion coefficients, just try the best of your memories. Spencer, try to be more specific, not just total energy operator, but dependence of energy on K parameter. Like, is it linear or quadratic or something different? And for the, I do not know who is on number 5, but this unknown class D completed eigenfunction, completed eigenvalue. And I think there is a little challenge for several of us to place the okay. Some of us have already completed. Okay. And everything we do is done by humans for humans. So do not waste your time on making calligraphy or advanced Greek symbols. You can just type error HO for row, or if you want some symbols, you can use substitute use different letter. It will be fine. If you okay. You can e to the power, and the main question like which power of K? It's 14. Yeah, second power, and the width parameter in the nominator. Very good, very good. Okay, and I guess number 5 is August. Is it correct? Okay. yeah. I recognized you by style of equations. And Spencer. No. Here it shouldn't be H capital. I would put H bar, which is like this H, which is crossed and is equal to 10 to the minus 34 joules per second. So now the only missing part is expansion coefficient. So we are almost done. August is done. Team is done. Jared is done. So for Jared, if you are putting this I T, and then H. Okay, yes, correct. Yes. H bar in the first power, K in the second power. Yes. Very, very good. I should say excellent. Okay. Then done, chair done, T done, August done. Spencer.
Yeah. Whatever.
Spencer, their suggestion is there should be exponential somewhere. So this exponential coefficients have Gaussian profile. So keep trying, and I will try myself putting nearby. Actually, I would be able to type things here. So yes, QRT is good. So pi sigma, and then exponential of what? Minus k squared sigma divide sigma naught divided by 4. So Jared, well, not Jared, sorry, Spencer, I think in the way how you write it, there's the exponential is missing. So let me touch the place you are typing and put it this way. Exponential, and then minus, and then this k squared delta, and over 2 over 4, it is not a big deal. Make sense?
Yep. Thank you.
And it could be pi here if you carefully take the integral, but it doesn't change the overall analysis of the result. So I think everyone is getting A for this assignment. Just as important who was participating. 1, 2, 3, 4, 5. Okay, good. And let me return to the slides. We still have about 5 minutes to conclude, but it looks like we are approaching the glory of the completion. So it is like how students from previous years were planning to put it here, and it is the equation that we are arriving at. I'm trying to be careful and put normalization constant up front, because again, having right constants is it's always hard to keep it, and always easy to make a mistake. And if you put just a constant and normalize it later, it will be safer. Now, exponential with wave function, linear in k. Then another exponential, which has imaginary unit and is quadratic in k. And then expansion coefficient that is also quadratic in k. So we do have 3 exponentials, right? And product of exponentials is exponential of 3 plus summation, right? E times e to the power a, e to the power b equals to e to the power a plus b, right?
Yes.
So here is our e to the power a, e to the power b, e to the power c. Now we can combine it into the one super exponential with just more arguments. And in the power of this exponential, we have a polynomial function of k, of this wave number, right? And our human patience is getting exhausted by writing long equations. So instead of repeating this exponential with all these little details, I can do it right away as e to the power minus something k squared minus something k linear. And then if we carefully analyze the arguments of each of these exponentials, we come that this b will be just minus ix. How can we see? It's just from the plane wave, right? So everything except k is minus ix. And for the coefficient in front of quadratic integration variable, we have minus sigma naught over 4 from your solution of the homework from expansion coefficient, and imagine a minus I h bar over 2mt for the phase accumulation due to Eigen energy. Okay? When we have a mathematical problem, in respect to integration variable, those are just coefficients. If I need to take this integral, I either look into tables, into internet, or just, if internet is off, trying to solve it by pen and paper. So 48 minutes, and I don't think we have anything else to say today. So many thanks for your questions. I believe we will have more fun later. Have a nice weekend.